All right. So this is where the point in the semester, I'm speaking to you guys, although you're not the ones I need to be speaking to. When I start to see attendance in the class go down, I start to see people fall behind. It's very easy for that to snowball. So good on you guys for being here today. I can't stress enough seeing me work through this stuff, being able to ask questions in class. I just see is if you don't do that, you're going to fall behind very quickly. So if you're relying on the recordings or things like that, maybe I'm speaking to those people right now. I would not plan for that to be my preferred option, right? Being in class is going to really help you kind of keep up to date and not ask questions where I'm like, well, I did that in class, right? Yeah.
I was wondering if you could maybe talk to us about how the exams are going to look.
So I'll talk a little bit about that if we have time at the end of the class. We're still a little bit further removed from that exam, but I can kind of mention it along the way with some other things. So before we kind of jump into material here today, what was due before we started class today? That first quiz, right? So that one was kind of, I shouldn't say easy, but there's a lot of review material, right? Stuff that you probably look pretty similar to things that you've seen in 370 or the equivalent. I would say for the exams, getting closer to the exam, I'll give you a practice exam. Very similar, like I give you these practice problems before the quiz. So they're pretty similar, right? You can kind of see, even if they're open-ended questions on the practice problems, and then they're multiple choice in the, on this quiz, it's the same kind of content, same types of questions. So I'll give you like a practice exam as we get closer to that midterm. So you'll have kind of an idea of what it's going to look like. It's going to be the majority kind of short answer. I think as we get further into linear regression, it's going to be out a little bit more. It's going to be easier for me to show you the types of questions I would ask you. Those in-class quiz questions, even if we go through them together, or I'm kind of, I'm presenting them to you and I'm giving, those are going to be good ones to go back to. Make sure you can kind of answer those. Now they might be a little bit more simple or easier, but sometimes I'll give some that are kind of difficult, and because I know we're going to talk through them, they're always good to go back and review those in-class questions that you see from these in-class quizzes as well. Right? It's a way for me to give you guys effort points, but it's also a way for me to give you just different examples of the types of problems you might see. So we'll see that on Thursday, likely some questions like that. Okay, wink, wink. Right. So what's due before we start class Thursday? That first problem set, right? So hopefully you've been working on this. I mean, you could have already probably had it all wrapped up. If you have any last minute questions, I'll post an announcement on Canvas. I might have to shift my office hours from the morning tomorrow a little bit. I'll be available in the afternoon ones. I might have to kind of shift those morning ones up. So it might be, instead of 10 to 11:30 and 1 to 2:30, it might be more like 12 to 3 or something tomorrow. But I'll get an announcement up when I have those exact times. I had a meeting pop up that I wasn't come up last minute that I have to transition some things over a little bit. So if you have any last minute questions, tomorrow, kind of early afternoon would be a good time to kind of stop by my office or send me an email here. So we're getting close to that due date, okay? I will also put up the next set of practice problems. So if we're going to the files tab, I'll throw up another folder. So I think here I just put it in week 1 materials. No, I didn't. Where did I put it? Got to be somewhere here. Did I put it in week 2 materials? Yeah. I'll kind of move these over to their own folder where I start to put up the practice problems that go with each quiz. So I'll put up the next set of practice problems. We probably haven't covered all the material for me to post the next quiz yet, but likely after class on Thursday, I'll put that next kind of second quiz up there. You can start to review those practice problems and think about taking that quiz over the next week and a half or so. All right. Also, after Thursday's class, I'll likely put up the next problem set. Once again, we probably haven't covered all of it, but you can start working on it early. So I put these things up not so that you do them the 2 or 3 days before the due date, especially the problem sets. I try to get them up early, even if we haven't covered every single question, where we can start to work on at least the ones that we have covered. Okay, so that's kind of where we're going this week. Any other questions from me before we jump into material? So we've got kind of week 4 here. We'll start in the slides. We'll have this next do file and data sets that we'll be using. But before we jump into material,
is it possible to go through like just 1 or 2 questions from the quiz that we just had to submit before class?
So generally, I don't do that during class, but if you have questions over old quiz questions, that's a good thing to kind of stop by office hours. We can kind of go through those. You can email me, I can answer via email, but yeah, office hours are a good time. Once again, if you can't physically be there, you can always send me an email and I can send you a Zoom link during those times and we can meet to cover them as well. But generally I try to reserve we got a lot of material, so I want to try to make sure we have enough time to cover that. If you have questions, overall quiz questions, things like that, that's a good thing to utilize office hours for, or after class. I'm always kind of here for a little bit afterwards if you want to kind of ask. Okay. If we have time at the end, maybe we will, but we'll see where we kind of go through stuff. Okay. All right. Any other questions from me before we kind of switch gears here? Okay. So I've got the next set of slides up. We're really going to kind of transition between talking about review and things that you might have heard mentioned. You might have, how many of you talked, did you guys talk about regression in 370? Probably towards the end. We're going to dive just a little bit deeper into it. So you might recognize some of these terms. Maybe a little bit of today's class will be a little bit boring or redundant, but we're going to start building on some stuff you probably didn't talk about in 370. Okay. So, whoops. There we go. So this kind of a review. What are we doing with linear regression? So we talked about one measure already, well, two measures technically, of trying to figure out what's the relationship between two variables. We said we could measure the what? Covariance, or if we scale the covariance, that gives us a correlation or correlation coefficient. So when we're talking about regression, we're essentially going to start out being able to identify a better version of the correlation coefficient. That's what we'll call it for right now. So, in general, we want to know as X goes up, does Y tend to go up? Does it go down? Or does it not change? Well, why do we want to know that? Well, because if I say have things like, I know it's going to be a colder than average winter. If I'm a propane company, maybe I can predict then the prices that I can get away with charging my consumers this winter. Right? I know they're going to need more or less. So we want to try to use these regression results eventually to start to make predictions, right? If I can understand the relationship between these two variables, when one of them changes, I can start to predict what's going to happen to the other one. You might think of, price and quantity demanded, right? If we're going back to like introductory micro stuff. So what we're going to do is really at its core, we've got a simple linear equation. In math, they always do what? Y is equal to mx plus b, right? Well, we're just going to call these something slightly different, right? Our b, we're going to call beta 0. This would represent the what? In an equation, this constant would represent the y-intercept. I'm seeing some people mouth it, right? What would beta 1 or m represent? The slope between this x and y variable. At its core, that's all we're doing with simple linear regression, okay? So some terms I'll start using. This y variable, right? It's going to be what we call the dependent variable. It depends on, or it's a function of x, right? So y is the thing that's depending on x, right? Or x is our independent variable. X is changing, and as a result, that y variable is going to change as well, right? So you could, think of any things like, if we start to change the price, or sorry, well, yeah, you can really think about that. If you start changing the price, what's going to happen to the quantity demanded, right? Now we're going to look at more interesting variables, I think, than just price and quantity. Well, that is interesting, but we're going to have some, I think, more interesting examples. So what we're going to do is try to figure out, based off of the data, what is this relationship between X and Y? So if I were to just look at a data set, and I had, let's say, I don't know, looks like about 30 observations here, I'm just going to plot every single observation. That would give us something we've already talked about, which I had a question before class, how to do this in Stata. We can create, what would this be called? A scatter plot. So on the homework, all I want you to do is give me the line of code that would create that. You don't have to like copy and paste the picture or anything like that, okay? So because we know what a scatter plot is, right? If I were to draw a line that kind of best fits this relationship, what would this line look like? Kind of downward sloping, right? So I would say that when X values are higher, the Y values tend to be lower, right? That's all we're really doing. We're trying to figure out, based off of the data, what is a line that would best fit the relationship in the data between this X and Y variable, right? So when we draw this line, if I had, a different one here, and I'll save this drawing for later. So let's say I had something that looked like this. That's my scatter plot. If I were to draw a line that best fit this data, it would look something like this. Right? I guess I should let's label my axes here. So if I had this line, it's going to have some intercept value, right? And I could calculate the slope. Ultimately, we said that's what we wanted with our linear regression, is to come up with a intercept and slope that best fits this relationship between our x and y variable. Okay. I don't think I'm breaking news here. Is everyone okay with this? Okay. So just to kind of be complete here, we can kind of go through some examples. You know, if I drew a line that best fit this data set, well, now my intercept is going to be up there, and my slope here is going to be negative, right? But a downward sloping line. So I've got different relationships. Maybe I had scatter plots that look like this. If I've got a horizontal line, what's that slope? 0. So that would mean that there's no relationship. X can change wherever it wants to, and I'm still getting about the same y values. Okay? We could have a positive relationship, right? Now, this positive relationship and this negative relationship I've drawn linear, right? This equation I gave you was a linear relationship. We are not going to, so negative linear relationship. We're not going to talk about these yet, but a little foreshadowing. We can actually, once we have a good understanding of our toolbox with linear regression, we don't have to keep it linear. We can actually make it nonlinear. So did you guys talk about these at the end of 370 or no? I think some people do. Some people kind of hand wave over them. We'll dive deeper into them really after the first exam, right? So we can have nonlinear relationships, but for now, we're keeping everything linear. We don't have to worry about those yet, right? So I'll give you examples where we're just going to estimate this nice linear curve. Okay? So what we're doing with the data, and we draw in this line that best fits the data, right, is essentially what we're trying to do, and I'll skip ahead here, is once I have this line of best fit, the actual x and y values are the observations that are plotted. So what this line is telling me is that if I put in different values for x, that's always going to correspond to the same y values on that line. So what my linear regression kind of line of best fit is actually telling me isn't the actual y values, it's telling me my predicted y values, and we'll call that y hat. So our line of best fit will, for different x values, give us a different predicted y values. Okay. Well, this seems like it might be something that's useful, right? Based off the data, I now have a line that best fits that data, and for different values of x, I can now predict what the y value would be. Now, the problem is for any one of these observations, so let's choose this one. What's true about the actual y value relative to the predicted y value at that point? If I were to take the predicted y value and subtract the actual y, what's going to be true about that? Well, the predicted value is greater, right? So here, we kind of think about this as going to be greater than 0, right? Now, what we'll end up doing, and just to kind of paint this out, it gets a little bit tricky, but when we're talking about our error term, we're going to call this kind of epsilon, right? Let me make sure I have that notation. Yeah. So epsilon, we're going to define a little bit differently. I think intuitively, you might think about taking the prediction and subtracting the actual y value. Our error term, or epsilon, is going to be the actual y value minus our prediction. So it gets a little bit kind of counterintuitive. But here, if I'm taking the actual y value and subtracting the prediction, here, what's going to be true about my error term? My prediction relative to the actual y is a little bit too high, right? So I'm actually going to have negative errors. Now, if I think about another observation, like over here, there, if my error term is the actual y values minus the predicted, actual y value minus the predicted y value, for this observation, my error, the actual y, is going to be what? Greater than my predicted y. So my error is going to be positive. Okay. Any questions on this idea before we keep moving here? Yeah.
So we just get our predicted Y values from this one.
Yep. Once we have this line of best fit, and we haven't talked about how we get it yet, but for now, it's just like we're eyeballing it. We'll talk about it a more technical way. My errors I could come up with an error for every single observation, right? My predictions are always going to be a little bit off. Technically, we could have a perfect prediction, but it's very unlikely that that's going to be true about most of our observations, right? The actual Y values are going to be just slight, even if it's to the second, third decimal, they're going to be a little bit off, right? So every observation, we're coming up with pretty good predictions. Notice, what's the difference between our predictions and the actual values? It's pretty small. It's not like we have a line that's up here and all our predictions are really, or have huge errors. We're trying to get this line so that the errors for every single observation are relatively small. That's why we're trying to draw a line that kind of best fits our data. Any other questions on this? Okay, so to be complete here, I call the error, and we'll use the error the way that it's usually notated in economics in most places, which is this epsilon, this Greek letter. If you were to look at the Stock and Watson book, they call this U a lot of the times. It's just it's just notation, right? It's just putting some letter that means the error term, right? So if you look in other resources, sometimes they'll refer to the error as epsilon, sometimes as U. We're going to always use epsilon. Okay? I like it because epsilon E looks like air, right? And that's not just me. It's a convention, but that does help. Okay. So I kind of already drew this out for us, right? But for any one observation, the difference between our actual and our predicted Y, that's going to represent the error that we made for that specific observation. Okay. So some of our errors will be positive. Some of them are going to be negative. So what we're going to try to do with linear regression is how do we find the intercept and the slope that would give us this line that minimizes how many of those errors we're making? Now, what is that really saying when we say we want to minimize the errors we're making? Well, we want to minimize our errors across every single observation. So for example, when I'm choosing my line of best fit, if the majority of my observations are here, I'm drawing this line that kind of minimizes, like, on average, if you want to think about it that way, the errors I'm making. Just because I have like one data point that's way up here, I don't want to then draw my line of best fit that's greatly influenced just by that one data point, right? So what we're trying to do with our line of best fit is minimize the errors that we're making across every observation. Okay? So some of those will have positive errors, some of them will be negative errors, right? Now, the reason why we don't want to just minimize all of the errors, so if we say all of the errors, really what I'm saying is I want to minimize so I'm going to try to minimize the sum starting with the very first observation, and if we did this with a population data set to the very last, right, of all of our error terms. Now, the problem is if I add up all of these errors, right, some of them are positive, some of them are negative. I don't care which direction I'm really making my errors. I just care that I'm making an error. So what are two ways I have of kind of getting rid of the sign of that error? Yeah, I could square it or take the absolute value. What we're going to do, because it has another feature for us with linear regression, is we're going to actually minimize the sum of the squared error terms. Right? So every observation, we're going to be making an error. We're then going to square that value, add them all up. Okay? We're then going to try to minimize the sum of all of those errors squared. Okay? Now, what does squaring the error also do? Excuse me. It would really overpenalize what? So if I have 1, let's say my error is 1. When I square it, what gets added in here? 1 squared is 1. If I have 2, when I square that, 2 doesn't get added in, 4. So when I have larger errors, what's getting added in here? Even larger values. So by squaring it, we not only kind of deal with this sign issue, we don't care which direction we're making errors, it over penalizes really bad errors, right? Which ultimately we're trying to make predictions, so we don't want to make really bad errors. So we're going to minimize the sum of our squared error terms, just to kind of give that. I think I've got this in a slide, but sometimes it helps, I think, to see things work through. And in general, we don't have population data. Usually we only have sample data, right? We're basing this off of a sample. Now, what's a way I could rewrite my error? We said it was the actual y values for that observation minus the predicted y. So we're kind of doing this, right? Well, what's another way I could rewrite my predictions? We said earlier, that's my line of best fit, right? So what I'm going to do is just substitute in here, how am I making my predictions? Well, whatever this intercept and slope are that give me this line of best fit, those should be the values that give me these predicted y values. So this would be kind of what we're trying to minimize. So whether or not I'm trying to maximize or minimize something, this goes back, I'm not sure everyone's math background, but these values, that's just whatever they are in the data. These are given, like this is what it is. We're not choosing these. When we draw a line of best fit and we're trying to just eyeball it, really the mathematically correct way to come up with what that line of best fit is there's 2 things that we don't know. We don't know the intercept and we don't know the slope. So if I've got a function and I want to minimize it and I have 2 unknowns, what would I do? Take a derivative in respect to the 2 unknowns. I would then have 2 equations, 2 unknowns. I can solve for what those values should be. Now, we're not going to do the derivative every single time. We're not going to want to derive this function every single time twice and then kind of solve for what beta 0 and beta 1 are. So people have already done that for us. So this is kind of what I had written up there. So 2 equations, 2 unknowns. And apparently I have an animation turned off, right? But if you were to do that math, and here we'll start putting in these values for the slope and intercept. I'll put a hat above those as well to say these are just the estimates for what that slope and intercept should be based off the data that we had, right? So based off the data we had, what are the intercept and slope values that would give us our predicted y values? So kind of like y hat, we're going to just use kind of little hats there to represent these are the estimated intercept and slopes from our data, okay? Now, what it ends up being, so ignore this part for a second, the numerator is the sum of the difference between every observation's x value and the mean times every observation's y value and its mean. What does that look pretty similar to? The numerator of our, so we don't remember it yet. This is why we do review at the beginning. So I've got the difference between x and its mean times the difference between y and its mean divided by the difference between x minus its mean, and then that not squared, sorry. Nope, I want you guys to, there we go. Yeah, squared, right? What does this look similar to? Well, if I was to just divide both of these by n, did I change this equation at all? No. What is this? If it's the deviation of x from its mean for every observation times the deviation of the y value from its mean, that's our covariance, right? Between these 2 variables. What is this? If I take the deviation of every x value from the mean squared, add them all up, divide by n, that gave us our, well, here I've got variance, right? Sorry, forgot my square, right? So really, if we have a simple linear regression, all we're doing when we come up with this line of best fit, the way that we calculate what that slope should be it would be the covariance between those two variables divided by the variance of our independent variable, the thing that's changing on our x-axis, okay? And I'll prove this to you with data here before we get out of here today, okay? All right. Any questions on this before we keep moving? Yeah.
So, and then we get this equation from deriving,
Yep. We're trying to minimize the sum of our squared error terms. Take a derivative of this in respect to the two things we're trying to find. Solve for this first one. We can then also solve for the second, which should be, let's see if I can remember this from memory. I think it's, will end up being this. Right? So let's see. And I'm not going to make you do that math every single time. In fact, I'll give you these equations when we get to the exam. You'll have a formula sheet, and these will be two of the formulas on it. So we had two equations, two unknowns. We can solve for what those would be. Okay? Now, how are we coming up with those? We're using the actual data, the actual x and y values, right? But we can always find what that intercept and slope would be that gives us this line that minimizes the sum of our squared errors. Yep. Excuse me. Any questions on this? Okay. Just looking kind of familiar a little bit. So we already talked about the numerator is the covariance, the denominator is our variance. So let's look and see how do we do this stuff in Stata, right? Oh, there we go. So the do file that we're going to be working with is this regression in class S25. So I started adding some things in I didn't from previous semesters. So we're going to just use that do file. So let's see, I think this is the global path that I want. So once again, yours is always gonna be different. Notice this is the one when I'm on my desktop computer. This is the one for when I'm in here in class. So I put them both in there. All you have to do is put wherever your file path is right here. And then this file, everything should kind of update, right? Wherever you're putting that data, which this week's data is the fracking data, and we're gonna use the COVID County data, put those on whatever folder in your OneDrive, copy and paste your global path. Right? If you're still having issues with that path, once again, you can always just manually go to File, Open, and open up the DTA file if you want to do it that way. Right? So once I do this, hopefully I have it in the right place. Yep. I'm going to go to this data browser, right? That was the magnifying glass. So I had a bunch of data here. It was like different counties, different years. Looks like only a couple years. I had the number of births in that county. And this is going to sound like a goofy example, but I got it from looking at something or some paper. This is the total number of shale wells. So a lot of these are zeros, but here you'll see like they have oil shale wells, like in some of these counties, like Texas has a lot of them. So there's this thought of like, are all these oil wells like bleeding into the drinking water? And is that impacting fertility in these different counties? That's an actual question researchers have asked. So this was a data set that was aimed to get at that. So we already looked at how we create a scatter plot. So you can do it manually if we go up here and you were wanting to do graphics, you can go two-way, choose scatter, choose the variable you want to be your X, choose the one you want to be your Y. However, the syntax that we're going to use is always the same. So I use this two-way. I want to make a scatter plot. Here's my X variable. Sorry, here's my Y variable. Here's my X variable, right? So total shale wells is the thing that I think is going to be independent. It's the thing that's changing my X value. As it changes, I'm thinking the number of births in a county is going to be responding to it. So the number of births was my Y value here. So I'm going to run this, and Stata should spit out at me. Probably too many observations. There we go. Okay, this isn't a great scatter plot. So the ones that I'm drawing in, it's usually very easy to see what that line of best fit is. It's not always easy to see what the line of best fit would be. Right? And we'll, in fact, talk about why this example, there might be some other things we want to do here in a second. Okay? So I don't know if I'm looking at this, maybe it's positive, maybe it's like most of these are zero. So I don't know, maybe there's no relationship. It's kind of hard to say. So instead of just eyeballing it, let's actually run a regression. Okay? So if I want to get this line of best fit, instead of doing the math, instead of deriving it, solving that equation, plugging it in, every observation, subtracting the mean, doing all, we don't want to do that by hand. People used to have to do this by hand. It took forever. That's why if you look at like data, if you look at research papers from like the 50s and 60s, the sample sizes are pretty small. Why? Because I'd have to go through and do this for every single observation, take the deviation from X and the average, multiply the deviation from Y and the average, add them all up. That's cumbersome, right? That's my GAs are doing that. But if I have, these nice data management programs that have a lot of computing power, I can do that very quickly. So this reg command, it's built in that Stata takes that equation we had to find that slope coefficient, right? That was like the predicted beta 1 value. It also has that beta 0, the intercept equation that was a little bit easier, right? We took the average Y minus the slope prediction times our average X. And it does all that behind the scenes for us. Now, it's going to do a lot of other things that we'll eventually talk about. But for now, so notice there's a lot of statistics up here, right? If I run that regress command. Now, the first word that I use, that's always my Y or my dependent variable, just the way we would write out the equation. Second variable is always our X or our independent variable. So what this is telling me is the slope coefficient, or that beta 1 value, is negative 3.9. It's also telling me my intercept coefficient, and I will admit, I say intercept a lot. Stata calls it something else. It's just synonymous terms. It's the intercept or the constant. So it kind of calls this underscore cons, right? That's just the way that it defines it. So our intercept coefficient, right, is going to be about 6,145. Okay. So very quickly, Stata does all this math behind the scenes for us and gives us the intercept and the slope that would give us our line of best fit. Okay. So based on the data, these are my intercept and slope values. So I'm going to write this down and well, I don't even have to do that. Let's go over here. Let's say I was going to write this out. I've got what? The number of births is equal to 6,145 minus 3.92 times the total number of shale wells, right? So we can just plug in these estimates we now have, and this is our line of best fit. If I want to make predictions for any county, let's say this is old data. Let's say I wanted to make a prediction for this next year, and they've got, I don't know, 20 shale wells in this county. Plug in a 20 here, and I can come up with the predicted number of births that I would see in that county. Okay. So just a really simple linear equation here. So what is this telling me? That if there's more oil shale wells in a county, what's happening to the number of births in that county?
It's decreasing by about 4.
It's decreasing, yeah, by about 3.92 births. Okay. So the way that we'll interpret these slope coefficients, it's always the change in our Y variable from a 1 unit increase in our X variable. What are the units here? Well, this was just the number of shale wells, so it'd be 1 more oil shale well. We'll talk through some other examples here in a second where we think about different units. Okay. Everybody with me up to this point? Yeah.
Why are there 2 error terms on the table?
Over here? So we haven't talked about those yet. So we got to walk before we can run. But we'll eventually get there, right? In fact, we should be able to get there before the end of class. So some other things I just wanted to show you before we get there. I also told you that this slope coefficient should be the same as the covariance divided by the variance of our independent variable. So in this case, how would I find the covariance between these two variables? Well, we already talked about that. That was our correlate command between these two variables, and then comma, we only wanted the covariance, right? So if I hit this, I get my covariance between the number of births and the total number of shale wells in the county, negative 303. Okay. What if I wanted to get the variance of my independent variable? Well, I can just use the sum function. I'll put in comma detail because I think if I just do sum, it gives me the standard deviation. I was lazy, I didn't want to square it. So if we do that, my variance is 77.4. Well, if I have the variance of my X variable and I have the covariance between my X and Y, if I take the covariance and divide it by my variance, sure enough, what value do I get? The same value I was getting for my slope coefficient. You can enter this into your calculator if you want to prove it to yourself, but it is, right? Negative 303 divided by 77 is negative 3.92. Or I'm rounding, so it's going to be approximate, right? So even if we don't want to run this regress command, we could actually find the covariance, find the variance of our X variable, and we could reproduce what that slope coefficient is as well. Okay. Any questions over anything here? So you'll kind of notice we're using things in Stata and what we're talking about, stuff that we've already talked about in the past, and we're kind of building on, right? We're talking about covariances, we're talking about variances. Yeah.
We're entering one way function, does it matter like the order and the two variables?
No, not for this, right? It's just going to tell you the correlation between those two. Yep. Now it does matter when I'm running the regression, right? Because then I'm setting it up incorrectly as x being a function of y as opposed to y being a function of x. Yep. Any other questions before we keep moving here? Okay. And I'll get to your question. I'm not sidestepping it for no reason, right? All right. So we'll go through a few more interpretations, and then I think hopefully we'll get to this idea of what does it actually mean? Why do we have other statistics in that output? Okay. So here was kind of my actual y values, right? When I'm making my predictions, I was only using the x values and these slope and intercept coefficients, but every observation we said, whatever my predicted y is, there's also going to be some error term. So the actual y values that I observe in the data set will include my predictions plus the error that's specific to that observation. Okay. So for example, if I'm trying to predict income based off of the number of years of education, for most people, their number of years of education will give me a pretty good idea about what the error won't be that large. But if I try to make a prediction for Bill Gates, if I put in his years of education and just try to predict income from that, we're going to have a huge error term for that observation, right? So every observation has its own error term, okay? Which is why we write this epsilon I, right? Each observation has its own error term. So in general, I already mentioned that our slope coefficient, this beta 1, the interpretation is the predicted change in y from a 1-unit change in x. Okay? That's the general form we're always going to use. So what about beta 0? So our interpretation will get a little bit weird sometimes, but if you were going to try to tell me what is beta 0, how would I interpret that just in general? That's the predicted y value when what? X is equal to 0. So in my other example, it would be the predicted number of births when the number of oil shells is 0, is how I would interpret that. Okay. So let's get a little bit more practice. So here I had another data set that I found at one point I thought was kind of interesting. 5,000 people. It was older, and it was it's from it's called the National Longitudinal Survey of the Youth. So it's like younger people. So notice the average income is pretty low. So it might see it's kind of outdated. I think this was from 1979, I believe, is when the survey started. So I also had kind of the marijuana usage or self-reported, right? So I had this idea of, okay, I'm going to try to predict an individual's income based off of their marijuana use, right? At least for this data set that I had. So here, this is the number of days they use marijuana each month. Self-reported income was their actual income over the year. Okay? So how would I interpret my slope coefficient here? So this is my regression. Now, I only did this for a singled out a year here. And it wasn't from 2010. This was the people were they did the survey in 79 and then they had the people later on. So it's just 1 year of data. You can kind of ignore that, right? But how would I interpret my slope coefficient here?
For each marijuana day, your median income or your income increases by 250.
Yeah, so we're looking at the observations are at the individual level. So it's when self-reported marijuana increases by 1 day a month. That was my unit of the X variable. The predicted income would fall by $253. Okay. Now, how would I interpret my intercept or my constant? This would be the predicted income when someone's using marijuana 0 days a month. Yep. So it gets kind of weird with some of these. These ones, I think it makes sense. I try to choose ones with the intercept don't seem too weird. Some of the examples we'll get are going to seem kind of weird, but that's still how we interpret our slope and our intercept, okay? Questions on this before we keep moving? Okay. Excuse me. So we kind of already went through this. This is just kind of a slide you can go back to. We just talked through this. So I had another example where I had some data from over COVID. Over the COVID regime, whatever we want to call it. So this was county level data, and it was the percent of that county that was vaccinated and the number of cases they had per 1,000 people. So if I run this regression, how would I interpret my vaccinated variable? Remember, it's a 1 unit change in my X variables. How would I interpret my slope coefficient on that X variable? What's a 1 unit change in the percent of a county that's vaccinated? I literally just said it. If the percent of a county that's vaccinated goes up by 1%, it's already measured in percentages, that's the unit. What is the expected change or the predicted change in the Y variable, the number of COVID cases per 1,000 people? For every 1% more of my population that was vaccinated, the number of cases per 1,000 people fell by 0.25 people. Now, this might not seem like a lot, but, if we're talking about states that have millions of people, that equates to be a decent number of people, right? So this is kind of our basic interpretation from simple linear regression. Okay. How would I interpret the constant here? So it's the predicted Y value when what? X is equal to. So how would I interpret this in this example?
0% are vaccinated, we expect 50.92 COVID cases per 1,000.
Exactly. When my X variable, the percent of the county that's vaccinated is 0, nobody gets vaccinated. The number of cases we expected per 1,000 people was 50.9 people. Okay. Any questions on that before we keep moving here? So just getting more examples, getting practice kind of interpreting these estimated slope and intercept coefficients. Okay. What did I say here? Does the percent? Okay. Oh, so this is where we start to then think about the magnitudes, right? Does this seem like a pretty large effect, right? Well, if I get 1% more of my county vaccinated and per 100,000 people, it's only going to decrease the number of people by 0.25. To me, that seems like a relatively low magnitude, right? That'd be like what? So 1% would be 10 people. So I'm at like, well less than 1%, right? It's not going to have a huge impact. So we also care not just about what the effect is, but the magnitude, right? We want to start to think about these examples. Is it a large magnitude and effect? So for example, if I use marijuana 1 more day every month, my income's going down by predicted $250. Is that a lot? Seems kind of like a lot, but at the same time, if I light one up Sunday morning, like I'm probably not getting a lot done that day. I'm probably not going into work or being very productive, right? And so, these magnitude of these effects, we'll start to think about this as well, okay? So that's just a couple examples. We're then going to look at this in state. Let me make sure there's nothing else. Yeah, we're going to talk about R squareds here. I really hope we get to your question because it was a really good one. But if we don't, it's okay. We'll get there Thursday. So I'm going to scroll down here. Since I already have my file path kind of set up, I'm going to go to the next data set, okay? Instead of this total shale well, oil shale wells, I'm going to use the county data, COVID county data. So I'm just going to open that data set up. We already looked at this in the slides, right? I'm going to have a different one, though, where I kind of show you sometimes these intercept coefficients get to be weird. So before I even run this regression, here I was using the number, just the raw number of cases, right? In what, October 2021, and the population of that county. So what do you think is going to be true about the sign of my slope coefficient? So how would I interpret if this population is like the number of people in a county, this is the number of cases, what should be true about that slope coefficient? If I have 1 more person in my county, yeah, it's likely going to increase the number of cases I see. Now, one thing we haven't really said yet, we're just interpreting just the slope coefficient. If I want to make predictions, I can make predictions for any number of increases. If I know the effect of 1 unit, So the effect of one more person, let's say, is having one more person in my county increase the number of cases that my county could expect by 0.13. Okay, so what if I have another 10,000 people in my county? What's the increase in my predicted number of cases? This is the effect of one unit. The effect of having 10,000 more units or 10,000 more people. That times 10,000, right? We're keeping everything linear, okay? So we can always scale up this effect to whatever we're interested in, right? Okay? How would I interpret, this is where the intercept will get kind of weird sometimes. How would I interpret my constant or my intercept coefficient here? So this is the predicted Y value. So the predicted number of cases in October 2021 when my X variable is equal to 0. So
I think it's saying that there's gonna be -16 cases per population this year.
yeah, right. So when my population is 0, the predicted number of cases are -16.7. How can you have a negative COVID case? Well, if we think about what we're doing with this line of best fit, so this was my population. Guess we're doing different colors. This is like the number of cases. It's likely, right? I'm not seeing counties with 0 people that live in them, right? So I could end up with all of my data kind of lies over here. So if I'm drawing a line that best fits this data, where is its intercept? It's going to be negative. Well, that's because I know that I generally don't have populations in a county that are less than, I mean, I don't know what the lowest populated county is, probably somewhere out in Wyoming, but there's probably still thousands of people in it, right? So sometimes our intercepts are a little bit weird, but it's because we don't often see a county that has a population of 0. It's like a hypothetical that doesn't really exist in the real world. Now, that doesn't usually take place with our slope, but it can take place with this intercept just by the nature of what a linear equation is going to do, okay? Any questions on this before we keep moving? Does that kind of make sense what I'm getting at there with kind of these weird interpretations? Now, something else I wanted to point out at this point. So let's go back and we'll do the number of cases per person, right? And I'm going to look at the regression between that and household income, okay? So I'm going to run this regression. So how would I interpret, and this is the household income, the median household income in that county. How would I interpret this slope coefficient? So what's a 1 unit change in my X variable? I'm fine with awkward sign. I'm not asking hard-hitting questions here.
What's the units?
Yeah, so if I have household income, this is from the US, I should have specified. What are my units of income? Dollars. So what would a 1 unit change be here?
0.0004.
So the unit change, though, where we start out is, what is a 1 unit change in my X variable? A 1 unit change would be if on average, the median household income in a county goes up by $1. That's a 1 unit change, right? So we start out, it's when the X variable changes by 1 unit. How do we measure income? Dollars. So a 1 unit change is when the median household income goes up by $1. The predicted or expected change in our Y variable, number of cases per 1,000 people, goes down by 0.0004. Yeah. So what's the magnitude? Initially, it might seem like this is a really what? Large or small effect? Small, but what's an increase of $1? I mean, when you look across counties, their average incomes can vary by thousands, right? So sometimes when we have these variables, to give us coefficients that make a little bit more sense, because when we're comparing counties, very rarely is it just like, oh, this county is, just $1 wealthier than the other. If you look at like Orange County and some of the other Northern California counties, there's significant differences there. So what we can do with our variables is we can actually scale them if it makes sense to have the units in something else. So instead of dollars, to me, it seems practical that it's very likely we would see like thousands of dollar differences in these counties. So all I'm going to do is generate this new variable, right? So we've talked about creating new variables. I'm just going to create this new variable that's equal to the median household income, but I'm going to divide it by 1,000. So what is a 1 unit change now in this new variable? What would that represent? So we can kind of think about this. If I divide income by 1,000, if I look at the data here, so where's income? Where are you at? Here it is. So 58,000, if I divide that by 1,000, becomes 58. So now a 1 unit change in this new variable I've created doesn't represent a $1 increase, right? Going from like 58 to 59 actually represents a $1,000 increase, right? So I can scale my variables so that the unit changes are different, right? If I scale this by 1,000, now my 1 unit's not just $1 more increase in my median household income. It'll be an increase of $1,000. So what should be true if I run this regression with my new variable? Instead of seeing 0.0004, that was the effect of $1. Now a 1 unit change will be having an additional $1,000. So the coefficient I should see should be what? That same value, but not divided by 1,000. Be careful, right? My 1 unit change now isn't $1, it's $1,000. So is the effect of a $1,000 change going to be larger or smaller than the effect of a $1 change? Larger. How much larger? 1,000 times larger. So what would I do? I'm going to move that decimal 3 places. So if I run this regression, unless I'm lying to you, my coefficient I get with my new scale variable should be negative 0.4, right? So sure enough, if I run this regression with my new variable, I get negative 0.4. It just scales that coefficient. It's not going to change the value underlying it. It's just that I'm changing the number of units that my X variable is changing by. Well, it's still 1 unit, but that unit represents a larger amount now. So you'll see this done a lot with income, populations, because back to my other example. Okay, well, if the population is changing by 1 person, we know the effect is going to be pretty small. So if I want to know the effect of $1,000, I could do the same thing, but create this new variable where I divide the population by 1,000. Now every unit represents a change of 1,000 additional people in that count. Okay. Any questions on that before we keep moving here? Okay. So we got 20 minutes. What do I want to do here today? That's an interesting example. Really wanted to get there today, but I don't think that I'd be able to complete it. So we'll go back. We'll introduce another idea, and then I'll give you a slightly different regression we'll talk about as well. So before we go back to Stata, kind of bouncing back and forth to give us a little bit of taste of both. So when we run these regressions, I can come up with these predicted slope and intercept values. But some relationships are going to be weaker than others, right? So if I think about if I run a regression where I'm looking at like the number of COVID cases, and I run that on, I don't know, average height, I can come up with a slope coefficient there. Like there's a value that would be the relationship between those two things. But do we think that the average height in a county is really going to be influencing the number of new cases? Probably not. Right? Now, if I run that same regression, the number of cases, and I have the population, well, what should be really indicative of the number of cases I see in a county? How many people are living there? So that relationship should be a lot stronger. So this measure of how strong the relationship is, we can kind of think about this as our R squared, right? So I think the book might call it coefficient of determination. I'll probably never call it that. It's just not the verbiage I use. But what the R squared represents is the percent of the variation in our dependent variable that the independent variable explains. Or, said differently, what amount of the variation in Y does our X variable explain? Okay. So if two variables are more related, having information on X should allow us to explain more of the variation that's existing in Y. So higher R squareds generally tell us there's a stronger relationship between this X and Y variable. Okay. So how do we calculate the R squared? So I'm going to skip ahead here. Ultimately, we're going to take this thing called the explained sum of squares and divide it by the total sum of squares. So I'll give you some intuition behind this. We're never going to have to do this by hand. But if you think about it, here's my predicted Y values. Here's my average Y values. How am I coming up with those predicted Y values? From my line of best fit, right? My linear regression equation, which we were taking the intercept and slope coefficient values, and I was using the different values for X for each observation to come up with the predictions. So this is going to represent how much variation exists in the Y values that I'm predicting using only this one X variable. So this is going to represent how much variation exists just in the predictions that I'm making with this X variable. So it's kind of like what is the amount of variation that exists in Y that is coming from changes in X? What would my denominator, the total sum of squares, represent? Well, if I look at the difference between the average and the actual Y values, that's telling me all of the variation that exists in the actual Y values. So the numerator is essentially like how much variation exists just from this one X variable that I'm using to predict it relative to the total amount of variation. So our R squared, I say that it's going to tell us the percent of variation that we explain. Technically, our R squared, even if we could explain all of the variation with one variable, what would my R squared be here? Anything divided by itself is 1, right? So it does represent the percent that we can explain, but it's actually in proportion, right? It's in the format of a proportion. So we can always go back and forth. So if I had an R squared of 0.5, what percent of the variation am I explaining with this one X variable? If the proportion I'm explaining is 0.5, the percent of the variation I'm explaining is 50%. So, right, it's always going to be kind of in decimal form or somewhere between 0 and 1, but we can always kind of talk about it in terms of percentages by just moving that decimal 2 places, right? Going from a proportion to a percentage, okay? So let's look at some of those regressions that we're running. I won't jump back to Stata, but just show you what Stata gave us, okay? So we had the oil shale well example with the number of births. So even though we found a negative relationship between the number of oil wells in the county and the number of births. So someone might say, well, look, yeah, we got to stop using these shale wells to get oil because it's decreasing fertility in these counties, right? Well, yes, that is the relationship, but what percent of variation in the births does the oil shale wells in a county explain? So I've got this R squared up here. Out to the 4th decimal, what is my R squared? 0, right? So you'd have to go out more than 4 decimals. It's going to be something slightly above 0, but it's so close that to the 4th decimal, it gets rounded. Basically, are oil shale wells explaining any of the variation, or are they explaining a large amount of the variation that exists in the number of births? No, they're explaining almost none of that variation. So we would say this is even though we can estimate the relationship and it's negative, it's a very weak relationship, right? It's going to be the number of oil shale wells in the county is a very small predictor about the number of births. Now, what if instead I had that percent vaccinated, right? Well, here, my R squared is what? 0.04. So just the percent of the county that's vaccinated, nothing else. It's explaining how much of the variation in the number of cases per person in the county, or per 1,000 people in the county. It's explaining what percent of the variation? Yeah, 4%. Proportion that it explains is 0.04 or 0.042. So we're explaining 4.2% of the variation in the number of cases in this county is just explained by the percent vaccinated. So it has a little bit more of a strong relationship there. Now, we can also use this. What percent can we not explain about the number of cases in the county, that aren't related to the number of percent of people that are vaccinated. We can't explain 96. So what does that mean? There's a lot of other things that are influencing the number of cases other than just the percent of the county that's vaccinated, right? So we can start to use these R-squared measures, and this is probably a little bit of a lazy way to say it, but intuitively, I think it's a way to remember it. A higher R-squared essentially means that your predictions are more valuable or more likely to be close to the actual Y values, right? That the amount of the variation in the Y variable you can explain is higher just with this one X variable, okay? And we'll break this down. We'll poke holes in that as we progress through the semester. But for now, we can think of it that way, okay? And then we can kind of grab, just to kind of point this out. So I said the R squared is the explained sum of squares over the total sum of squares. Stata also gives those to you. So here, kind of this model SS, that's the sum of the squares that your model explains. Our model is just one variable up to this point. So our model, the one variable we're using, here's the amount of variation that exists in our predictions. Here is the total amount of variation that exists, or the total sum of squares in the actual Y values. If I wanted to reproduce my R squared, I would just take the sum of the squares, or the variation that exists from my model, divide it by the amount of variation that exists from the actual Y values, and that should give me this 0.04. You can kind of reproduce this on your own if you really trust me or something, but right, that should be what you get. Now, there's another piece of information given here, which is this residual sum of squares. So what do you think that probably represents? It's the amount of variation that we can't explain, right? So if I left this out, how could you find my R squared?
Subtract.
Yeah, if I know the amount of variation I can explain, divide that by the total, well, then the amount this is the proportion of the variation I can't explain. So if I want to know the proportion I can, it would just be 1 minus that. So just to kind of reiterate this here. Our total sum of squares is our explained sum of squares, or in Stata, it kind of calls it the model's sum of the squares, plus our residual sum of squares, or what we can't explain. So, anytime I know any of these, I can kind of think about, I can find the others. So I know that if I were to take all of this and divide it by the total, right? This would be 1. I know that 1 is equal to, this was essentially representing our R squared. And here, this was representing, we didn't really have a statistic for it, right? But if I somehow knew the residual sum of squares and the total sum of squares, I could kind of back out what my actual R squared was. Okay? So those points, or those values are also given to us in that Stata output. But in general, we're always going to have the R squared in that output, so we can always just go there and look for that. Okay? But just kind of piecing together, thinking about sometimes, we are interested in how much we can explain, but sometimes we're also interested in how much we can't. Like in the COVID example, I think it's interesting about how much we can explain, right? So that probably means, and we haven't progressed this far, although next week we definitely will, if there's still 96% of the variation I can't explain, what do I probably want to do? Go out and get more data or variables other than just the percent vaccinated, right? And then I want to use multiple variables to try to predict my Y. We got to walk before we can run. We're starting out with just using one variable, okay? Any other questions before we keep moving here? All right. So we didn't quite get to your question, so I apologize, but there's something else I want to show you guys before we end class today. What we'll talk about next class is what do these errors next to our estimates mean? And basically, it's going to be very similar to what we were doing with the distribution of sample means. Because when I come up with these slope and intercept coefficients, they're just based off of one sample. So if I take different samples, I might see slightly different estimates for these slope and intercept coefficients. What do you think is end up going to be true about the distribution? If I were to take like 1,000 different samples and run 1,000 different regressions, all those coefficient estimates, how do you think they're going to be distributed? Normally. And what are they going to be centered around? So with our means, our sample means we're normally distributed around our population mean. So our sample coefficients are going to be normally distributed around the true coefficient or the true relationship between this X and Y variable. So we're going to be rehashing, reusing a lot of things this is why I took the first 3 weeks to like build up a lot of these principles. So now we can apply them to linear regression, right? So I got one more thing that we'll do in Stata before we get out of here. So I've got these R squareds in here. We kind of already looked at those in the slides. I want to go through one more regression just to kind of hammer home what we're doing, okay? So we talked about standardizing variables, right? So if I take my mean income, right, it's just going to be the mean across all these counties, every single county's household income. I'm going to calculate what that mean is. I'm also going to calculate the standard deviation. I'm then going to take every county's household income, subtract the mean across every county, and divide by the standard deviation. This is going to give me a nice standardized income value. So if a county had a standardized income value of 1, what would that really be telling me? That county's income is 1 standard deviation above the average income. Remember, this was in the US data, so 1 standard deviation above the average US income, right? If it was negative 1.5, it would be a county that has average income that's 1.5 standard deviations below the national average income. Okay? So if I'm going to run this regression, okay, and I want to say, can I predict, I'm thinking about people that had more money might be more or less likely to actually get vaccinated than those who didn't. So counties that maybe were more affluent, well, I don't have to worry about getting the vaccine that's experimental if I can, hold myself up in a multi-million-dollar home, right? If I have to go to work every single day still, right, be around tons of people because I only make $30,000 a year, I might be more likely to get that vaccine, right? So I'm going to use the standardized value of income here. So what would my interpretation here, let's think carefully, of my intercept coefficient be? So if I'm standardizing this value, oh, why isn't it switching over? There we go. So I had the percent of a county that gets vaccinated. I'm trying to come up with a slope and intercept value based off of this standardized variable of income. So how would I interpret my intercept coefficient? This would be the predicted Y value, or the predicted percent of a county that's vaccinated, when what? The X variable is equal to 0. What would an X variable being equal to 0 be here? A county that has the national mean income, right? It would be 0 standard deviations away from that national mean. So what should this really represent? This should just be the mean vaccinated, right? So we can actually look at this. So if I run this regression, right, I say, okay, for every standard deviation a county had income above the mean, they're actually increased the percent of that county that got vaccinated by almost 5%. So this was like wealthy people getting the vaccine, or wealthier counties more likely to get the vaccine, I should say. Okay. Now, I said this constant represents what the mean vaccinated should be when the standardized income was 0, or we had the mean. So notice here, if I summarize this vaccinated variable, what value do I get? That intercept, right? So the average percent of a county, across the entire nation that got vaccinated, when I standardize that income variable, that's essentially telling me when that county had average income, what was kind of that vaccine starting at. Remember, what did we say was the equation for our intercept coefficient? This. So if I standardize this variable, the average X would be 0. That's why my intercept coefficient was simply the average Y value here. Now, I might not like quiz you on this specifically, but it is something like that kind of ties together a lot of the different concepts we're talking about and kind of gives us this connection between really what we're doing when we find these intercept and slope coefficients and thinking about the interpretations that we have. Yeah.
So when we're doing the other interpretation,
Mhm.
because it's like tricky with units, because
Mhm.
z-scores, they don't have units, correct?
Well, technically they do.
Okay.
So what does a z-score represent? That's our unit. So it'd be if I'm one standard deviation above the like national level income, my county has a one standard deviation higher average income than the nation. 5% approximately of my county got vaccinated. Yep. And then you go the other direction too. If my county was impoverished, 2 standard deviations below me, about 10% less of my county got vaccinated. So, if I was trying to tell a story, this is where we won't go down this road, but you use this data to try to think about, okay, what does that mean? So what is this really telling me? Counties that were wealthier were getting vaccinated at higher percentages. Counties that weren't as wealthy, getting vaccinated at lower. So this might tell me a couple things. Either lower income counties just don't have access to this vaccine, or maybe, I'm going out on a wild limb here, maybe individuals who are lower income, what might they not trust as much? The government, right? And so maybe they were less likely to get the vaccine. So now, obviously, this isn't a complete picture, but this starts to give us a first glimpse at what's going on between these two variables.
Okay, just to clarify, so when we're standardizing our X variable, it essentially just tells us that our y-intercept is equal to
Our y-intercept would be equal to the mean of that y variable.
that y.
And then we move from that point in either direction as that X variable goes up or down from 0. Yep. Now, we don't in practice, you don't do this all the time. Although it makes sense in some contexts to standardize. So a lot of times, what's something that gets standardized a lot that you might have the data already standardized? All of you have taken them. ACT tests, SAT tests, right? A lot of the times, instead of the numbers, the data will come in as already standardized, right? Minus the mean divided by the standard deviation. So we have a lot of data that is already standardized, which is why I bring this up at this point. Because yeah, we generally don't just all of a sudden create this new variable that's standardized, but a lot of times the data will just come into us already standardized, in which case we can think about what a regression using it would actually mean. Let's see another hand. Okay. So before next class, like I said, you'll likely see the next set of practice problems and the next, I might even put the next problem set up. I know that the current one isn't due until we meet in class on Thursday, but I'm going to try to get it out there early so you can start working at it. I don't know if I'll get it up before I leave today, but for sure tomorrow when I'm in the office, I'll get that next problem set up. Okay. Other than that, I think if there's anything else I need to mention, should be good. I'll see you guys on Thursday.